Okay, you can start.
We are on live, sir.
Okay. Yeah. Okay. Good evening, all my dear colleagues and my dear students. Today we are here to have a discussion on why to learn high frequency techniques. And to deliver the talk, we have Professor Dr. KP Ray. KP Ray sir is an MTech in microwave electronics from the University of Delhi and PhD from the Department of Electrical Engineering at IIT Bombay. Presently, he is a professor, director, School of Radar Technology, and head of the Department of Electronics Engineering, Defense Institute of Advanced Technology, DAIT DRDO, Pune. Before joining DAIT in 2016, he was the program director of Samir, Mumbai, wherein he joined Samir TIFR in 1985 and worked for over 31 years in the area of electromagnetics, RF, and microwave engineering, microwave system and component designings, developed enterprise in this design of antenna elements. He also have an expertise in design of antenna elements, arrays, and high power RF microwave sources for radar, scientific, and industrial application. He has successfully executed over 50 projects sponsored by various government agencies like DRDO, MOD, ISRO, DOS, DAE, DST, MEITY, DBT, IMD, BHEL, etc., and many in the capacity of main designer, a chief investigator, and a project manager, etc. Recently, he developed a microwave sterilizer named Atulya to neutralize COVID-19 viruses. We are really grateful to you, sir, for giving us the time and accepting our invitation to discuss about the most difficult and the most challenging part of in the engineering, which we always ask a question: why to study electromagnetics? And student always have a question, or we always have a question, that why we should study an electromagnetic engineering. What is the benefit of learning electromagnetic engineering? Because going through the curriculum, it always gives us a feel of that it's another mathematical subject rather than getting into the concepts of that subject. So it will be really grateful to hear from you that yes, why we need to actually study high frequency techniques and how they are helpful in a day-to-day life. Over to you, sir.
Okay, thank you so much for the opportunity to share some of the concepts which has been gathered over the years. You are able to hear me? Are you
Yes, sir.
able to hear
Yes, sir.
me?
We
Yes,
are able to
yes,
hear.
yes, sir.
Yes, sir. Yes, sir.
Okay, so I thought we will discuss today that why one requires the basic concept of that high frequency technique. By high frequency we mean that it is RF frequency. It also includes microwave and goes beyond millimeter wave to terahertz. So this total frequency spectrum is known as high frequency. And then the concept which is used by in low frequency circuits, those things doesn't become applicable at high frequency. Now, till a very recent past, maybe till I can say that till 2000, uh, all the domains were very distinctive. Like if someone is working in computer in the field of computer or designing some PCB for computer, he was categorized as computer engineer. Or someone who is working in digital signal processing, he will design a board, FPGA board or a microcontroller board, and then he will have his own design methodology, and he is categorized as a digital person or signal processing person. Likewise, if someone is working in frequency less than 1 megahertz, he will be using all these breadboards, and then also PCB he will make, which will be a glass epoxy substrate, and he will not be concerned about the track width and also about the track of the length. So all these fields were well defined, and there was no overlap. But now in the present day scenario, when things are, the boundaries are becoming blurred, and one uses a clock speed of something like 1 Gbps, data rate of 1 Gbps, or clock speed is going up to sort of, gigahertz range. And there is also concept of in the digital signal processing, or if you have received some high frequency or mega gigahertz frequency signal, you try to first down convert the frequency and then you process. But then the concept of direct processing, the RF signal has also been employed. So when the clock speed is going in gigahertz range, and also that data transfer is going up to 1 Gbps, 2 Gbps, then you cannot work in isolation. you know so even the computer engineer dealing with that faster clocks, or data speed, or digital signal processing person directly digitizes the RF signal and processes at baseband itself rather than down converting that one. Then you need to know what are the technique used in high frequency. You know so so I thought I'll share some of the things with very informal lecture using this that scribbling pad which I have here, and some of the PPTs also I will use in between. Now, coming back to high frequency, how we define high frequency. The screen is visible to you. Is the screen visible to
Yes,
you?
yes, sir. Yes, yes.
Okay, so this covers the whole electromagnetic spectrum, starting from a signal with frequency of 1 hertz and going up to cosmic rays. And right now for today's presentation, we will not go beyond infrared. You know, there is a boundary here which separates these millimeter wave and high frequency going up to the low frequency, and here the terahertz frequency comes in between. And to have a larger bandwidth, now people are not only talking about terahertz, people have started using terahertz. So from here to low frequency, we will be concentrating today. So when we say high frequency, in this lower frequency side, which is also known as power spectrum, where the wavelengths will be in thousand of kilometer here. And then comes the band, which is in a very generic word term, we call them radio waves, and that includes the AM band, FM band, and also it goes, there is no hard and fast boundary, but then the radio wave starts from the AM band and then extends beyond. Some of the books, Russian books, the RF frequency includes from 1 megahertz which goes up to terahertz frequency band. So very selectively people use this lower spectrum of microwave as RF band, and then they go to microwave, and then when the wavelength becomes in millimeter wave, uh, then that is known as millimeter wave, and then terahertz starts, lower end of this optical domain. That is known as here terahertz. I mean, in some of the books you will find that total frequency spectrum is known as RF, but in India we refer to lower band of the frequency lower than microwave as RF frequency. So we have one around 1 megahertz is FM band. We know that around 100 megahertz is FM band, and then we will see what is VHF and UHF frequency band. So today when we refer to high frequency, we will be referring beyond maybe 100 megahertz, and then that will go up to terahertz. Now to discuss this frequency band very precisely, I will come back to the design example, but then before that, why even digital people or computer scientists need to know the high frequency technique. I will come back to that main topic of today later. First, let me introduce this frequency band. So when we are telling high frequency, it starts maybe we can say that it starts from maybe FM band and goes up to terahertz frequency band. Now we when the I mean, when the broadcaster, in radio, when they broadcast, they call meter wave. I mean, you all of us, we know that term meter wave. What is meter wave? Meter wave, where wavelength is it starts from some a fraction of a meter, goes up to maybe 10 meter or 100 meter. That frequency band we call meter wave. Likewise, when you see that when the wavelength is in millimeter, then that is known as a millimeter. Now, this microwave frequency, there is a myth in associated with this terminology. There is nothing micro about microwave. That will be clear when we exactly come to this frequency band. So I will go to the next slides, and then we will introduce. So this is the frequency band what we will be referring to as high frequency band, and techniques which are used in this frequency band we call high frequency technique. So we will quickly see this frequency band. HF frequency band, that starts from 3 to 30 megahertz. VHF is again 30 to 300 megahertz. UHF is 300 to, some books say 1 gigahertz, some books say 300 gigahertz, and beyond that this microwave frequency band starts. And then when the wavelength becomes in millimeter, we call that as a millimeter wave frequency band. Now if you concentrate in this microwave frequency band, if you will see that wavelength will vary from if you concentrate from 1 gigahertz to, let us say, 100 gigahertz, wavelength will be nicely represented in centimeter. So basically this frequency band, which is loosely referred to as a microwave frequency band, is nothing but if you follow the nomenclature of when the wavelength is in meter, we call that as a meter wave. When the wavelength is in millimeter, we call that as millimeter wave. So likewise, if you follow that convention, then microwave should be in a technically correct manner will be defined as centimeter wave and not microwave. So then why do we call this frequency band microwave? Because if you recollect, of course, wireless communication was demonstrated by Professor J.C. Bose, and he used millimeter wave frequency, and which was recognized of, I mean, very late. But then this wireless technology was demonstrated by Marconi, and probably he used AM band to communicate from UK to Canada. So that he used a frequency band where the size of the antenna used to be much larger. Likewise, transmitter and receiver, we had those gang capacitors, and then size used to be much big. So the system which were designed, those wireless systems which were designed initially, the size of those systems used to be much larger, you know. So with respect to that, when these microwave components, that size of the components is comparable to a wavelength at that particular frequency. So when one started designing these components and system in microwave frequency band, that becomes a miniaturized, much miniaturized version of what Marconi's systems were there. So that's why micro word is associated with miniaturization, and that's why that word is given as microwave. There is nothing micro about microwave. Many times we misunderstand that wavelength is in micron. It's not micron, it's in centimeter. So technically correct representation of microwave is centimeter wave. Now, having said this one, that what are the high frequency techniques, and I mean, what are the high frequency regions. Now we will come back to today's lecture, and I will try to I mean, put across the concept through this some of the examples. So let us take first example. First example of frequency. Maybe we will go for 100 kilohertz. That frequency we will go, just to demonstrate you how the concepts of Ohm's law, Kirchhoff's theorem, all those things fails, at high frequency. Here, when you take the example of, uh, I mean, of course, they don't fail, but then they are not complete to represent the high frequency circuits. These Ohm's law that gets modified, Kirchhoff's law, Thevenin theorems, that also gets modified. So that we will try to see through these examples. Now, if you take a frequency, of that 100 kilohertz, what will be the wavelength? Wavelength is a spatial characteristic of any signal. You remember that. So this lambda, which will be represented here by a crest and trough, this is how we represent lambda. Now if it is 100 kilohertz, then what will be the wavelength? 10 to the power 8 meter per second, divided by 100 into 10 to the power 3, and this will be in meter. So this one will come out to be 3, you can say that 3000. I mean, so it will 10 to the power 5. So this one will be 3. So this becomes 3000 meter, that will be equal to 3 kilometer. That is the wavelength. Now, when you say, I mean, of course, people working in digital domain or computer domain and also low frequency domain, they know that the concept of Ohm's law, Kirchhoff's theorem, Thevenin's theorem. So there, how the Ohm's law is defined. We say that if we have let us say source of our battery, you can say, let us say 3 volt, and then we have a resistance here of, let us say 3 ohm, whatever. So the current which will be flowing here is 1 ampere. This is how the Ohm's law is introduced to us, and so, and we deal with this as 3 volt, this is 3 ohm, this one is 1 ampere. So here we deal only with amplitude. We deal with only with amplitude. Why? Let us say this circuit which I have drawn here, what will be the size of this circuit? I mean, I have just drawn here to show you the concept of Ohm's law. Here, or you can put this as a source, you want to be more inclusive, and that is 3 volt, let us say, voltage source. So the 1 ampere current flows here. We are only talking in terms of amplitude. Why? If you try to represent this circuit in this wavelength, which is 3 kilometer, this circuit anywhere depending upon the phase, here, this circuit, if you are representing here, it will not be even a dot, because size of this one will be how much? At most it will be, let us say, 20 centimeter. I mean, not more than that, 20 centimeter. And 20 centimeter circuit you are representing in terms of wavelength, we call that electrical length of the circuit, that is negligibly small. So this one, there is no spatial variation of this dot which is being represented by the circuit. So then the amplitude there is fixed. So there is no variation because electrical length is so small of these electrical circuits or electrical components. We only deal with amplitude. We only deal with amplitude. 3 volt, 1 ampere, and the electrical value of this resistance is lumped around this in this area, and that is 3 ohm. So we talk only in terms of amplitude at lower frequency. And how do you define power transfer from these things? When your source impedance is R plus jx, we define that maximum power will get transferred if it is complex, load is complex conjugate of these things, complex conjugate of the source impedance. This is how the maximum power transfer theorem is defined, MPTT. So these things. Now let us take another example, and so you will see that why even digital people or computer people working in computer domain or signal processing people, they need to know the concept of high frequency. Why? That we will demonstrate. Let us take frequency of 10, we will take, let us say, 3 gigahertz, 3 gigahertz frequency. So what will be the wavelength? 3 into 10 to the power 10, 8 meter, divided by 3 into 10 to the power 9, 10 to the power 9, that hertz. So then this becomes how much? This will become 10, 1. So this will become 0.1 meter, or this one will be 10 centimeter. 10 centimeter. Now when you design a circuit, and wavelength is 10 centimeter, then if you see the wavelength, full full 360 phase variation, that is corresponding to lambda. Here, I mean, 360 phase variations was getting realized in how much? 3 kilometer. Now if you see here, if I have a circuit, let us say here, which is 5 centimeter input and output, 5 centimeter. So then it represents almost 180 degree if you see, if you compare in terms of wavelength, it is lambda by 2. Now here, when the signal is traveling along the circuit, then it is also undergoing phase change, because now the insertion phase of the device, unlike in this case, which was negligibly small, because it had negligible, you know, negligible, what do you call, electrical length. Now it is comparable to wavelength, very much comparable to wavelength. So in Thevenin's theorem, you have seen that all currents are coming and then they are getting added here, and then we never discussed that what is the length of the path. In Ohm's law also, we were not bothered about, what is the size of the PCB, or side of the circuits. I will give you example. I mean, most of the time in our BE experiments, we are asked to design a common emitter amplifier. So for which we are given a breadboard, a transistor 2N22 will be given, 222 will be given to us, and there will be some jumpers and some capacitors, resistors, they will be given to us. And then when we make a circuit, it will be working. But then when teacher comes in nervousness, we will stop putting some of the connections in the breadboard, and it doesn't work. And then when you try to figure it out that why it's not working, and then you realize that you have missed a jumper, what do you do that time? You take a small piece of wire, and use your teeth as a cutter, and chop off the plastic portion of that wire, and you make a jumper, and then you put between 2 points, and then circuit gets completed, and then your common emitter amplifier, maybe in kilohertz frequency range, start working. So what is the why I'm telling that, when you are making a jumper or you are making a interconnects, you were not bothered about the thickness of that interconnect. You were not bothered about the length of the interconnects. Why? Because frequency is small, and electrical length of that jumper was negligibly small. So you are not concerned about the insertion phase of this small components. Whereas now, let us say you have been asked to make a power combiner, and then like here, I mean, that ampere circuit law and all those things you were doing, and then directly current were getting added. Now let us say you want to make a power combiner, and then you are not bothered about the length of this one. And if you take this length L, and by mistake you have taken length this plus 5 centimeter at this frequency at 3 gigahertz, then what will happen? This signal coming here, and this signal, there is a path difference of 5 centimeter, and that path difference of 5 centimeter gives the phase difference of 180 degree. So instead of having this here power P1 and power P2, corresponding voltage you can find out, and they get added here. Instead of getting to, let us say P1, and this is a combiner, instead of getting power as 2P1, you will get zero power. Why? Because they will cancel, they are out of phase. There is 180 degree phase difference, because 5 centimeter is corresponding to that 180 degree phase difference. So instead of getting a double power, you are getting zero power. You understand? So in the high frequency domain, you cannot neglect the insertion phase of the device. Each one, here breadboard you are using, here you cannot use that concept. So along with the magnitude of the vector, there will also be a phase, because when it is passing in the circuit, at each point the phase is changing. Why? Because electrical length at high frequency becomes comparable to wavelength. So you cannot neglect that one, you know. So then how I am saying that you cannot, you need all the engineers working in the field of electromagnetics or computer, or even designing a digital card. They cannot avoid the high frequency technique. They need to you know that the consequences of how much length has to be taken, also consequence of how much width has to be taken, we have to take into account. Now we will I mean come to the actual these things, the representation. Now let us say your clock speed is in gigahertz range, or that repetition frequency, or you have a data rate as high as 1 gbps, 2 gbps. So effectively you are entering the microwave domain. So in that one, when you are even designing a digital card, you have to take care of two things, you know. When you are making a track, and where you are trying to take the high frequency part from that track, then you your here you have to always talk with respect to some reference. So if we have a two port device here, and then you cannot have any arbitrary point, you know, because the moment you change the point, your phase will change. So then this your that signal will also change, you know, signal will also change. So that's why in high frequency representation or high frequency techniques, we in the breadboard only we talk about input and output of the circuit. We the basic representation of the port is a high frequency technique, high frequency concept, because you have to fix the reference. You have to fix the reference for with respect to which you have to define the signal. You have to define the signal. And also at high frequency, you know, the transmission line concept, we talk in terms of characteristic impedance that we call Z naught. That is the reference, that is the reference impedance. So those type of things are not used earlier in digital domain, or for computer engineers, or a person who is only working in the low frequency. The concept of characteristic impedance is not valid for that. I mean, were not used extensively. Of course, it will be valid at lower frequency also. After all, in circuit theory, we say that Z naught is nothing but a square root of LC, where L is the inductance per unit length, C is the capacitance per unit length. So this is how we define here. So this is the input port, this is the output port, and we define a port here because the moment you go away, the phase of your signal will change. At high frequency, then at low frequency it was only represented in terms of magnitude. Now high frequency we have to represent in terms of magnitude as well as phase. So at low frequency, so then here this becomes that when amplitude and phase both are there, then that lumped concept where only the magnitude we were able to deal with, now that manifests into amplitude as well as phase. So then that becomes wave, so we earlier in you saw 3 volt, 1 ampere, that type of things we had only amplitude, whereas here, and when the correct now the characteristic impedance which is real, we generally take that as 50 ohm. So then your maximum power transfer theorem of complex conjugate here, r minus jx, now this term is not there, so this is 50 ohm, that Z naught is 50 ohm. So then maximum power transfer theorem at low frequency gets modified as matching these things. We talk that maximum power will get transferred when the reflection coefficient is 0. So here, if this is Z naught and this input impedance here, Z input here is also Z naught, then what will happen? I mean, this Z naught is equal to this Z naught, that is both 50 ohm. So maximum power transfer holds good, but we at high frequency we talk in terms of reflection coefficient. So this gamma becomes, here Z input minus Z naught and Z input plus Z naught. So then when Z naught Z input is equal to Z naught, so then reflection coefficient is 0, means everything is getting moving in the forward direction. So it all the power is getting delivered through this port to this device. Of course, ports can be only identified when it is TM mode. That details I am not going because it's a generic lecture. So here maximum power transfer theorem in high frequency gets gets modified to matching problem, matching problem. So when it is matched, maximum power is getting delivered to the load, and similarly that will be applicable here also. So that's why when this one ZL, ZL is equal to Z naught, then maximum power gets delivered here. Now when you have used a jumper in breadboard, you did not bother about the thickness of that breadboard, whereas here, thickness of the transmission line, that will decides, and configuration of this one, because thickness will decide the inductance, and also proximity of these two lines will decide the capacitance. Then that will decide the characteristic impedance. So then at high frequency, when you are using that clock speed or that high data rate, it is a microwave or high frequency problem. So in that case, you cannot have these things any thickness. That thickness has to be selected in consonance with characteristic impedance, and that characteristic impedance for maximum power transfer to satisfy has to be equal, so that there is no reflection. So then when amplitude and phase both are there, we talk about forward moving voltage, we talk about reverse moving voltage, and we are still representing voltage and current, because that is how we have been introduced introduced to Ohm's law, Thevenin's theorems, Kirchhoff's theorem, these things, Kirchhoff's law, Thevenin's theorem, we still deal with voltage and current. Best thing for high frequency, we use electric field and magnetic field. Line integral of magnetic field is voltage. Closed loop integration of magnetic field is current. They are related. So best thing to deal with high frequency circuit is to deal with voltage and electric field and magnetic field. But since we are introduced the concept of voltage and current, then we still are comfortable to deal with that. So then any voltage which is there at port number 1, we talk in terms of V1 is nothing but superimposition of forward moving voltage plus reverse moving voltage. So when reverse voltage will be 0 when it is perfectly matched, then your V1 will be equal to V1 plus. So V1 plus is nothing but forward moving voltage wave. V minus, and like that current also, if you want to represent I1, because here that direction is important, so this will be I1 plus minus I1 minus, you know. So let us so you have to take care, because it becomes voltage wave and current wave. Now, if you we are introduced for at the low frequency the concept of Z matrix, admittance matrix. Transistors are represented by H matrix, you know, HIE, HOE, HFE, HRE. So those type of representation will not be directly valid at high frequency, because we have to talk in terms of voltage and current magnitude as well as phase. So then we talk in terms of scattering matrix, you know, scattering matrix. Now at low frequency, we have these terminating conditions, because either voltage for the impedance matrix voltage has to be 0. I mean, or for admittance matrix current has to, voltage has to be 0. For impedance matrix current has to be 0, because excitation is current for impedance matrix and excitation is voltage for the admittance matrix. And you can have 0 current or voltage when either it is for voltage it has to be open circuit, and for current it has to be short circuit. But if you do open circuit and short circuit, if you put here short circuit, this will be 0, this will be 0, then it reflection coefficient is 1. So then everything will get reflected back. So you need to have terminating conditions as characteristic impedance match terminated, so that there is no excitation here. So instead of using Z matrix, you know, Y matrix, H matrix, at high frequency it is a scattering matrix. So we talk in terms of S11, S12, S21, S21, S22. So this becomes then input reflection coefficient, output reflection coefficient. It is a forward gain, it's a reverse gain. So this one will be attenuation, it will be then the reverse attenuation for the passive device, and for amplifier it will be isolation between the two ports, and this one is the forward gain. So now let us generalize now. Now let us say you are designing a breadboard, you know, not breadboard, you are designing a digital circuit where you are using a high clock speed, you know, high clock speed you are giving here, or you are taking a high data rate here, you know. Now here you cannot afford to have any width of the transmission line, and also any length of these interconnects. You know, you are taking input and output here. This has to be matched to the impedance, input impedance, which is appearing at this level. Otherwise, if there is no mismatch, sizable amount of signal will get reflected back. Likewise, same thing happens here. So those people who are designing a digital circuit, which or a computer card, where you are dealing with high data speed or high clock rate, then you need to take care of the impedance matching here, impedance matching here. Also, you need to take care of what will be the insertion phase here, insertion phase here. Let us say you are taking two the data, high speed data, and you are not taking care of the proper length of this one, and then you are combining them, or you are processing them, and then you wanted them to add in certain manner, and then if they are one vector will be in this direction, other vector is in this direction, so then you will not have the resultant vector what you are looking for, that high frequency data here, you will not get the full data here, you know. And once reflection, then they creates lots of problem. There will be EMI EMC issues. There will also be now new this subject has been introduced, that is known as this that, you know, I mean, that signal integrity issues, you know. So you need to have a proper width, you need to have a desired length, so that you don't encounter any problem when you have designed a digital board which has got high clock speed or a high clock rate, or you have high data speed. So you need to take care of the impedance matching, that is high frequency representation of the maximum power transfer theorem. So impedance matching, that has to be done. And then second one is insertion phase of the device cannot be neglected, like how we did at low frequency. So these 2 points for for the scientists or engineers working in the digital domain, in the signal processing domain, or in the field of computer, when they are dealing with high clock rate and also high data rate, they need to take care of the high frequency technique, you know. So I'm sorry, I mean, we started late. Some of the scattering theory, I did not go into the detail, but then I sort of try to emphasize that even people working in digital domain or in the computer, you know, making a computer card, uh, uh, in the field of computer science and computer technology, where you are dealing with a large clock speed, I mean high rate, or high data rate, you won't be able to cannot, you have to use these concepts of impedance matching. You need to take care of the insertion phase, means the lead length, you know. If you have that this that output, if you are taking, let us say, uh, here RF output, and then this is uh, sort of the chip, or let us say some uh, uh, this FPGA board or microcontroller dealing with high data rate, then this matching here and also matching where you are connecting has to be taken care of, and also this insertion length of the track has to be accounted for. So I will stop here. If you have any questions, I will keep my breadboard open, and then we can discuss using breadboard. If you have any query, any doubt, so I will not be seen for you because I'm sharing this breadboard screen. Sorry, not breadboard, my scribbling pad screen. So you can ask me question now. I will stop my what do you call this interaction at this point, and I will take up questions.
Yeah, I request participants to put their questions in the chat box so that we can have a great discussion. If you have any queries, put it in the chat box. We will take up your queries.
Okay, then I will minimize. I mean, I will come out of this. I will
No
not.
problem.
Otherwise, I will not be able to read the queries which they are
Yeah,
putting
exactly.
forward. Yeah.
Sir, I'll assist you with the queries, so no worries. Sir, we have the first query from Abhishek Kalyankar. He says,
Okay.
Sir, is the impedance matching necessary even for flip-flops and counter circuits?
Yes, if this that clock speed is exceeding is in excess of, let us say, that that 100 or beyond, you can say, I mean, in a generic way, the 10 megahertz or 100 megahertz, you need to take care of impedance matching, and also you have to take care of the, because then that becomes high frequency problem. That depends on what is the rate. He's telling flip flop, but that I mean, if normal flip flop which you design, there you don't have to take care, because there the rate is not high. But then when you are designing higher rate or higher clock this frequency clock rate, you need to take care of impedance matching and also the lead length.
Okay, thank you for the answer, sir. Uh, Waiting for the next question. Okay, sir, I am very curious that you have actually answered a question of mine that was been asked to me by one of the experts in microwave itself, that why microwaves are called as microwaves. And I always keep on searching these answers, and none of the book actually give the appropriate answer for why they are called as microwaves, because the wavelength is somewhere in centimeters, but they are not at all in microwave. So, can you please repeat that why it is called as microwave, sir, for some of our students who have joined late?
No, you are telling that your concept became clear, or you want me to repeat that?
Sir, I want you to repeat for some
Okay, okay,
students who have joined
okay.
late.
I mean, this is what is this is how I view. You will not find in books. Some paper somewhere I got a hint and then thought, pondered over that point, and there is this. The answer is like this: that if you see in microwave frequency, wavelength is in centimeter. So when wavelength is in meter, we call meter wave. When wavelength is in millimeter, we call millimeter wave. So then why microwave are not told centimeter wave, are not called centimeter wave? Yes, it correct representation of microwave is centimeter wave. They, because wavelength in centimeter. You cannot use one nomenclature for one frequency band, meter wave, or other one as millimeter wave, and then microwave we call microwave. It is actually, it's a centimeter wave. But earlier people used to design a low frequency circuits, and size of the circuit, if you remember what was the size of a transistor, forget about transistor, transistor set. No, I'm not talking about three leg transistor set. It used to be a big volume. I was told that when this mobile phone was made, the size of the mobile phone was close to the size of a small room. You know, this so I mean that lots of miniaturization has taken place. But then coming back to your question, earlier the gang capacitors and all those things used to be much large. because most of the circuits were designed in low frequency. I gave the example of Marconi's experiment where gay wire monopole antennas were used, and it used to be huge. So the compared to those things, when microwave frequency range was people started getting using that, then size of the components becomes in centimeter or fraction of a centimeter, or maximum it will be 10 of centimeter, not more than that. So compared to those low frequency which were prevalent here, first time people when they broadcasted AM wave, and now AM wave is nothing but is around one megahertz, and you can imagine what is the wavelength, what will be the size of antennas, and then other related transmitter and receiver. So compared to that microwave frequency range, the size become much smaller, and micro word is related with miniaturization, so that's why name was given as microwave.
Okay,
Okay.
sir, that was a great answer, sir. And many of us now are in a state of answering that why they are called as microwaves. So there's one more question, which states that on what basis, probably on what basis, people would have thought that we should use microwaves, or what actually has given a birth to the use of microwaves.
Why people started using microwave?
Yeah. And
Yeah,
what was the
that
thought process, probably?
like that. If you see that this the JC Bose used millimeter wave, and that was the first wireless experiments. So human mind is very creative, you know. I mean, at what time they got triggering idea, and then they started using this one. But most of these circuits were developed, you know, I mean, these magnet the active components and all those things, radar, during World War II. They say that necessity is mother of invention. So I mean, like, you know, quest for you know, I mean, having a better system and having higher bandwidth and all those things, people moved to higher frequency, probably because at what time people started microwave, there is a radiation series, you know, that Montgomery's was one of the researcher, and then we have 10 volumes of radiation series. So microwave, these things are well documented in that one. If you see the historical perspective from the antenna point of view, you read JD Cross book, you will get lots of insights about why people started using higher frequency. Many of these things I mean, has been invented for radio astronomy, you know. So all those things were also you know, I mean, lots of applications were there. I mean, like that need to use higher frequency and all those things were felt, and that is how probably people have gone for microwave. That's a difficult question.
Okay, sir. So it was just a curious question about the historical development of this
You have a
microwave.
lovely dog at home. Yeah.
Sorry, sir, she's
Um,
disturbing us.
yes. I also
Okay.
have many of them in my house. So
Okay.
nice to see that you also have kept a dog.
Yeah, yeah, yeah.
You are a faculty. You are faculty in some engineering college.
Yes, sir. I'm faculty from Vidyalankar. Yeah.
Oh, you are a colleague of Professor Thakur and Professor
Yes, sir. Yes.
Deshmukh. Okay, okay,
Yeah.
okay.
So there's one more question from Abhishek Kalyankar. He asks, sir, if we run out of bandwidths, even in FM, can we use something else for transmission?
If
If we run out of bandwidths, even in FM, can we use something
no, I'm,
else
I'm
for transmission?
speak slowly, and please speak near the mic because you're
Okay. Okay. I'll repeat the question. Sir, if we run out of bandwidths, even in
run
FM,
out of run out.
bandwidth, bandwidths,
No, I'm not getting that word.
bandwidth.
Bandwidth.
Yeah, yeah, bandwidth. Even in FM, can we use something else for transmission?
You see that you require a bandwidth, isn't it? I mean, from communication theory, you know that you require bandwidth, you know. So otherwise, how the data will be, I mean, data will be sort of will be we will be put in a channel we call, isn't it? You know, and that has got the frequency width, like each channel is 10 kilohertz or 20 kilohertz, that sort of thing. So uh, yes, I mean, uh, for sport frequency, I mean, you can send the that data, but
Sorry, sir.
I believe that reproduction of that data in the other end will be difficult. Let us say
Sorry, sir.
you have designed a pulse of 1 microsecond, you know, and then you are using, you don't have bandwidth of 1 megahertz, and you are directly trying to send that one. Probably that will not be, you will not be able to reproduce that 1 microsecond pulse at other end. You know from the theory. So otherwise, then why people will crave for higher frequency to have much larger bandwidth? Faithfully reproducing the data with narrow band becomes very difficult. That I am not sure whether I have answered
I'm
your question,
sorry,
but this
sir.
is what came to my
I'm
mind.
sorry, sir. Thakur here. I'm sorry, sir.
Hello.
Sir, Thakur here. Probably the question,
Yes.
probably
हाँ,
he is
बोलिए
asking
बोलिए.
that our students'
Hello.
question could be put in this way, uh, that if suppose the FM band 88 to 108 is being exhausted, can by any other means we can send the information FM, that for music whichever we are using, that probably he is asking about. Not the band is
Um,
essential, that already you explained about.
no, but then, but let us say Radio Mirchi 92.4. Uh, so that is the center frequency. But then
Yes,
I'm not sure how much bandwidth is allocated for each of the broadcaster. So, I mean, you
200
require
kilohertz.
bandwidth. So, hello.
200 kilohertz it has been assigned, but their question, the student is probably asking about, if bandwidth is exhausted, can by any other means,
Ah.
no, that is what I understand, ki if the bandwidth is allocated, total bandwidth
No,
divided by.
so in the same bandwidth, we have all these communication technique. You use that phase aspect of the signal. You can have polarization aspect of the signal, so
Right.
that you using same bandwidth, you are able to send various signals, isn't it? That is how all those techniques uh, have been sort of uh, uh, proposed, and then they are being used also. So probably is that the answer?
Uh,
We hope
I
so
request
that the student.
Abhishek. Abhishek, can you please elaborate your question, or probably you can unmute yourself
He
and you
has
can
said I understood, sir. So I think he is
ask.
clear.
Okay. Okay.
Yeah, probably he has given up, because they got scared from the high frequency technique. Yeah.
Okay. Uh, yeah. So
Okay then.
yeah. So he said understood, sir. Okay. So
Okay.
being from antenna background, as a researcher from antenna background, people always thinks when we talk of high frequency, they always call off that it is about radiations. But we
Now. I am afraid now the communication is fading. I am not able to hear you. Maybe the network issue is coming here because the signal is very weak. Probably what you are telling is not getting reproduced. Of course, this is a high frequency problem. So it is becoming. Now I'm not able to hear you all. I'm trying to
Uh,
come to the screen, closer to screen, but then I'm not able to hear.
okay, so I'll repeat, sir. Whenever we think of or whenever we speak of high frequency, people always talk of radiation. But in high frequency, radiation is not the only
No, no, no,
concern.
no, 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 no. When we talk about high frequency, it's not radiation. Radiation is one of the one of the property. High frequency, you have so many non-radiating circuits. You have, so it's not only radiation.
Yeah. So
These
normally,
things.
yeah, normally
and
what happens?
and why radiation, I mean, why radiation from the circuits happens because you don't match it properly. That's why forward moving wave, reverse moving wave will get superimposed, and then that is how amplitude becomes large. Any mismatch, wherever you are violating maximum power transfer theorem, and which gets transformed to impedance matching in high frequency, you will have all these radiations because the signal is getting built up. So that's why it radiates, and also impedance matching, and also that you need to have that that signal in sync, I mean, like if you understand the two-wire transmission line concept, there is a return path there, and then most of the things get coupled, and we ensure that electrical distance between two wire is electrically small, so they are tightly coupled. Capacity of the line is large, so then there is no radiation there. So as long as line is balanced and then there is no mismatch, there will not be radiation from, unless you are deliberating want to radiate. Yes,
Yeah.
so
So there
high
is a myth.
frequency
There is
doesn't
all.
mean that radiation.
Yeah.
Yeah.
There is always a myth that whenever people speak of high frequency, they always talk of radiation. This is what a myth is among many of us.
Okay.
Yeah.
Okay.
So
Hope
there is always a myth.
clarified. Hope I have clarified.
Yeah, yeah, yeah. So it is
Okay.
very much clear to our students
Okay,
also now.
then they will here at 7 o'clock they close. I'm still in the lab, so
Yeah.
we will try to wind up now
Yes, yes. Sure,
because
sir. Sure.
already a reminder has come.
Okay.
So
Yeah, sir.
so
So,
so then
thank you very much, sir, for your great information exchange. And we have understood a lot of things about microwaves and what are high frequencies and why they are called as microwaves. And there were a lot of insights that were given to us that how the wavelength is important now comes into picture when we talk of high frequency. And that really has given us a new area into which we can work and explore towards.
but Professor Sekhar, I would like to say that idea was to put across a point to digital people, signal processing people, and computer science people, that when they design a digital board with high clock rate and then higher data rate, they need to understand the concept of impedance matching. Idea was not to introduce microwave. That Professor Thakur will do very nicely, So I thought that I will enthuse other students which are not working in the domain of microwave also to attend the class when Dr. Thakur takes the class of impedance matching and microwave. That was the idea.
So basically, sir, student actually have got to know about microwaves. They are always
Hmm.
afraid of microwaves, but now they have got to know that how to look towards the microwaves.
Then I
That is
could have oriented my lecture more towards microwave than trying to convince other domain people to use high frequency technique.
yeah. So they will surely work and explore more into this. Because of the short of time, we are now trying to capture as much as knowledge as we can. And but that actually has opened a realm of research in microwaves, and understand how microwaves can also be used in digital circuits. So thank you very much for your information exchange, and that was a really great session. And we have understood and have grasped a lot of knowledge in this new domain. Thank you very much, sir, for your time, and thank you very much for all the efforts that you have taken for us. Thank you very much.
Thank you so much, and thank you. I thank Professor Thakur who initiated this lecture, and finally Dr. Professor Deshmukh,
I'm not
Rambadas
doctor.
Deshmukh
I'm not.
has really sloged it out to catch. I mean, to locate me, and then he tried to solve the problem of these network issues very patiently. So thank you for everything.
Thank you so much.
So then I will sign off.
Yeah.
Yes, sir. Thank you very
Yes.
much, sir. Thank you.
Thank
Thank
you.
you, everyone.
Thank you. Thank
This
you.
is Ashish Shekhar signing off.